To close off this chapter, we are going to derive Kepler's third law for the special case of a planet that is in a circular orbit around its star. We will call the mass of the star big M and the mass of the planet little m, and we'll say they're a distance r away from each other. So we could look at this picture. We are assuming circular orbits for everything in this problem. And we could ask, what is the nature of the force that causes the planet to orbit its star? And the nature of that force is gravity. So if I apply Newton's second law, F net equals ma, I am applying Newton's second law to the planet. So I have the mass of the planet on the right-hand side, and I will talk about the acceleration of the planet. The force of gravity is the force that keeps the planet in orbit around its star. So I could write Newton's law of gravity, big G times the mass of the star times the mass of the planet divided by the distance between these objects squared, and that's equal to the mass of the planet times the acceleration of the planet. Now I could look at the orbit of the planet and recognize that the planet is moving in a circular orbit. So this acceleration will be centripetal acceleration. Another way we could see that, think about the direction of the velocity of the planet at any given moment and the direction of the force on the planet at any given moment. Right now, the direction of the planet's velocity is going to be something like this. But the force of gravity is always going to be attractive. So the force of gravity is going to be towards the star. The acceleration of the planet from Newton's second law is always parallel with the net direction of the net force. So that implies that the acceleration of the planet is going to be perpendicular to the direction of the velocity. There will be no tangential component of the acceleration of the planet. The planet will only have a radial component to its acceleration. Therefore, the planet's acceleration will be entirely v squared over r. So I could then write this as Newton's gravitational constant times the masses of the two objects over r squared equals the mass of the planet times v squared over r. At this point, we look at what we have here, and we could recognize we have the mass of the planet on both sides of the equal sign, so we could cancel that out. And here I have a 1 over r, here I have a 1 over r squared. So I could cancel the r on the right-hand side with one of the r's on the left-hand side. And I'll be left with Newton's gravitational constant times the mass of the star divided by the distance between the star and the planet is equal to the speed of the planet squared. Now what we're going to do is we will look at that planet's orbit, and because the planet is moving at a constant speed, we know it's a constant speed because no component of the acceleration is parallel with velocity. We could say that the speed of the planet will just be the distance traveled over the time of travel, which in this case, the planet is moving in a circular orbit. So once around the star will be the shape of a circle. The distance traveled would be the circumference of a circle. That would be 2 pi r. And the amount of time it takes the planet to orbit the star is going to be the period of the orbit, capital T. So I could plug this term for v in here and write g big M over r equals 2 pi r over t squared. Now, at this point, I'm going to simplify this term a little bit more. So I have a 2 pi, but I square it. That gives me 4 pi squared. I'm going to bring that 4 pi squared term downstairs to the left-hand side. And this r, I'm going to bring upstairs to the right-hand side. So what I'm left with then when I cross-multiply would be g big M over 4 pi squared equals r times r squared gives me r cubed divided by t squared. Now, let's look at this result. Let's think about what we did and why did we choose to write our result in this manner. Capital G, that is Newton's gravitational constant. That is going to be the same for everybody. That is a fundamental constant of nature as far as we can tell. There are mysteries surrounding G. One of the big ones is, why is G so small? But regardless, it is a constant of nature. For pi squared, those are just numbers. Those are the same for everyone. And within the solar system that we're considering, big M is the mass of the star at the center. Big M is going to be the same for every planet. So, which planet was I considering? Well, I'm going to ask, does it matter which planet I was considering? If I am considering planet number 1, then I could say, this is the mass of planet 1, this is the mass of planet 1, this is the distance from the star to planet 1 squared. Then I could just put all these subscripts 1 throughout my problem here. But notice that on the left-hand side of this result that we got, I don't have any subscripts. This just has to do with the mass of the star and some constants of nature and a number. If I consider a different planet now, let's consider planet number 2. So if planet number 2 is orbiting the star much closer, well, we could say planet number 2 will have a mass m2. It will be a distance r2 away from its star. It will take a length of time t2 for its orbital period. But if I were to go through this entire calculation again, I would end with the exact same result. All I would functionally be doing is just changing a subscript from a 1 to a 2. Everything else throughout this problem would be the same. The speed of planet 1, well, now I could talk about the speed of planet 2. The mass of planet 1, well, now I could talk about the mass of planet 2. Average distance from the star to planet 1, average distance from the star to planet 2. And I would end up with a result of big G times big M over 4 pi squared equals R2 cubed over T2 squared. Now, if I want to, I recognize the left-hand side of this equation is just going to be a constant. The left-hand side of this equation is that exact same constant. So I could then write this as R1 cubed over T1 squared equals R2 cubed over T2 squared. Now, at this point, I am going to change the notation that I'm using, but I'm not going to really change any of the physics that we're talking about. Throughout this problem, I said R was the distance from the planet to the star. I said T was the amount of time it takes that planet to orbit the star. But to align with what's written in the PowerPoint slides, I'm going to replace R, the distance from the planet to the star, with A. I'm going to replace T, the orbital period, with capital P. And when I make that substitution, that replacement, I get Kepler's third law as is written in the lecture slides. A1 cubed over T1 squared over P1 squared equals A2 cubed over P2 squared. So here we have derived Kepler's third law for the special case of circular orbits. To close off, I was talking about if we are looking at the solar system and suppose we want to know something about the orbital period or the distance from the Sun to Neptune or Venus or any of the planets. Let us choose Earth to be one of the planets we're considering. And let's choose the standard unit of time to be years, the standard unit of distance to be astronomical units. 1 astronomical units is defined as the Earth-Sun distance. So when I do that, I will say, let A be measured in AU, where 1 AU is the Earth-Sun distance, and let P be measured in years. And let's set Earth to be planet 1, because we're number 1. When I make that substitution, the average distance from Earth to the Sun is 1 AU. That is the definition of astronomical units. The average amount of time it takes the Earth to orbit the Sun is 1 year. And so I would have 1 cubed over 1 squared. And then I would have A2 cubed over P2 squared for whichever other planet we're talking about. We are comparing this other planet to Earth. Well, 1 cubed over 1 squared, that just gives me the number 1. So I could then write this line as 1 is equal to A2 cubed over P2 squared. And I could rearrange it to say P2 squared equals A2 cubed. And at this point, because we're talking about another planet in the solar system and we're comparing it to the Earth, we already set the distance from the Earth to the Sun to be the number 1, and the amount of time it takes the Earth to orbit the Sun to be the number 1. We just said the distance we're measuring in astronomical units and the time we're measuring in years, so we don't really need this subscript anymore. And we get a simpler version of Kepler's third law for when we're considering objects orbiting the Sun.